Good afternoon, everyone. I really think one of the next big advancements in database technology will be automatic indexing. Imagine if Postgres could tune itself based on your workload. I think it's much closer than you might imagine, and so today I wanted to walk you through two different approaches that I've taken to make this happen. And they're both available for you to use on your own systems and try out today. But first, a little bit about me. I work for a grocery delivery startup called Instacart. We do same-day grocery delivery from all your local stores, and we can do it in as little as an hour. In my free time, I like to do a lot of open source work. You can find me on GitHub under Kane. And one of my more popular projects is called PG Hero. It's a performance dashboard for Postgres. You hook it up to your database, and it tells you when there are common issues, and also helps you figure out how to resolve them. So it can be really helpful for types of issues that you haven't seen before. But enough about me. Let's talk about indexing. Why do we add indexes? Well, the reason is that we want to increase read performance. So we want to speed up our queries. And it comes at the expense of write performance. So inserts, updates, and deletes are a bit slower. And they take up space. So they take up space on your disk as well as in memory when indexes are hot. Right now, we're all doing what I like to call manual indexing. And the reason I call it that is it reminds me of cars. When you're driving a manual car, you're the one responsible for shifting the gears to make the car go faster. With an automatic transmission, we've taught a computer how to do that. The computer takes in all of this input from its environment and figures out how to shift based on that. What's the same in both scenarios, whether you have a manual transmission or an automatic transmission, is the underlying mechanism, the gears. And so I think we can apply this to the database. I think an index is a great underlying mechanism, but I think what we do need to change is who's adjusting that mechanism, who's operating it. And so we can go from having a human do it to teaching a computer how to do it. So in the first approach that I tried, I wanted to just mimic what I was doing manually when I was adding indexes to a database. And that looked a little something like this. First, collect the queries, so figure out what queries are running, and then analyze them. And from there, figure out what are the best indexes to add. And to collect the queries, there's this great extension that I'm sure many of you are familiar with called PG stat statements. PG stat statements keeps track of the most time-consuming queries on your database. And you get something that looks like this. You get the query, you get the total time that's been running, and the number of calls. And with a little bit of division, you can calculate the average time that a query is running. And that's really what we're most interested in for this approach. So if we look at the first query, its average time is just 0.5 milliseconds. So this query executes very, very quickly. So adding an index really isn't going to help this. Here we probably want to reduce the number of calls. For the second query, there are a lot less calls, so the average time is much higher. And so this is likely a very good candidate for an index. And let's say that the query is this one right here, a very simple query. Select star from products where store ID is 1. If we want to add an index here, we need to pull some information out of this query. And the two pieces of information we need are the table and the column name to index. So how do we teach a computer how to do that? There's this great extension, great open source project called pgquery that allows you to do just that. You give it a query, and it produces a parse tree. And from the parse tree, with a little bit of magic, you can pull out the tables and the columns that were used in that query. This project does it in a really neat way. It actually statically links against the Postgres parser. And the advantage of that is that it can parse any queries that Postgres can parse. So going back to our query, we can pull out products as the table name. We can pull out store ID as the column name. And now we have the piece of information we need to add an index. Now let's make it a little bit more complicated. So now we have a second condition, and brand ID equals 2. Now we have a couple more choices for an indexed add. We could add it on store ID again, we could add it on brand ID, or we could add a multi-column index on a combination of the two. Let's put multi-column indexes aside for just a second and consider store ID and brand ID. To make a good decision about this, we first have to understand what the underlying data looks like. Here we have stores that have many products. So a single store is going to have a lot of different products in it. And we have brands that are just going to have a few products associated with them. And now let's try to get an intuition about what column is going to be better to index by thinking about how the database is actually going to execute this query. So if we add an index on store ID, what the database is first going to do is it's going to traverse the index. The index is a tree structure. And it's going to find the location of all of the rows that have store ID 1. And then it's going to go fetch those rows. And that's what you can see here in the top. The rows in yellow are the ones that it fetched with store ID 1. And then it's going to filter on any other conditions. So here, brand ID 2. And what we end up with are the rows in the green. So this is the result of the query. If we add an index on brand ID, similar situation. It's going to traverse the index, find the location of all the rows with brand ID 2. And it's going to fetch them. And those are on the bottom in yellow. And again, it filters. And we end up with the data in green. So the results of the query are the same. So what's faster? And the answer is pretty straightforward. It's where the database does less work. So less work is going to be quicker than doing more work. And in which case did the database do less work? It was the second one. The database had to fetch less tuples. And so here, adding an index on brand ID is going to be the right decision. Now, how do we teach a computer how to do this? Luckily, Postgres stores information about the data in your columns, and it exposes this information with the pgstats view. And two pieces of information that we're interested in for the columns are the number of distinct values in the columns and the fraction of values that are null. And so let's see how we can apply those. Let's say our products table has 100,000 rows. And every product has a store ID, so none of those rows are null. And there are 100 distinct stores. If we query on a given store ID, we should expect to get 1,000 rows back. And this is what's called row estimation. If we look at brand ID, it's on the same table of products, so it has the same number of rows. This time, let's say that 10% of the rows don't have a brand for some reason or another, and that there are 9,000 distinct brands. Here we would expect to get just 10 rows back on average from the database. And so which is going to be faster, fetching 10 rows or 1,000 rows? The answer is fetching 10 rows. Now let's say that our data set's a little bit bigger. Let's say it's 1,000 times bigger, and that instead of 100,000 products, we have 100 million products. Let's say the other stats stay the same. This time we would expect to get 1 million rows back if we query on a given store ID, and we'd expect to get 10,000 rows if we query on a brand ID. And 10,000 rows is a decent number of rows. So can we do better? Can we have the database fetch even less rows? And this is where multi-column indexes come in. So the database can traverse an index on multiple columns, and so it has to fetch less. So what we do here is we would first find that brand ID is a better selection for the first part of our index. And then we apply this row estimation approach again. And this time we start with 10,000 rows. We apply it with any of the other columns that are also in the query. This time it's just store ID. And we end up now with just 100 rows if we add a multi-column index. And so here, fetching 100 rows is going to be much faster than fetching 10,000 rows. So we'd like to add an index, a multi-column index on brand ID, store ID. Let's take a step back for a moment and look at some other queries that we might want to optimize. So here's another common format of query. We have an order by clause with a limit. So here, adding an index on created at is going to speed up this query. And of course, we can combine these two together. And so here we have a where clause as well as an order by clause. So what we'll first do is take the approach we took before, starting with the where clause. We'll do row estimation to see how many rows we get back. If it's a very small number of rows, we can stop there because the database can sort those rows in memory. and return a result pretty quickly. If the number of rows is large, we again would want to add a multi-column index, this time on store ID and created at. And so this is the first approach. And this is the approach that you actually get if you use PG Hero and you turn on suggested indexes. So there's a page that shows your most time-consuming queries, and it'll look for any indexes in those queries, and it'll report them to you. And so here you can see that it's found 2 indexes on the most time-consuming queries. Now, there are a ton of shortcomings to this approach, and so I wanted to talk about just a few of them. One is that it only works on a single table, or it only works on simple queries, and the format is a single table with a simple where clause and a simple order by clause. So this is far from all of the queries that you want to optimize, and specifically, it doesn't work with joins. Also, we're duplicating some planner logic, and I use the word duplicate very, very loosely. People spent years and years optimizing the Postgres planner. And so this is just a very simple heuristic to try to get at just some of what it does. One of the reasons the Postgres planner can make even better decisions is that it uses more statistics that are available. So in this approach, we just use the first 2 listed there, but there are also many other statistics that the PG Stats view provides. And I wanted to spend just a little bit of time talking about what those are. So Postgres also stores the most common values for every column, or what it estimates to be the most common values. The PG Stats view is updated whenever you run the analyze command. So it's not continuously updated, but that command can typically runs enough with auto vacuum that you don't need to worry about it. And so here we can see that the most common values in our store ID column are 2, 5, and 1, and it stores their frequencies as well. So we have 90%, 5%, and 1%. And the reason it does this is that depending on the value that you query on, the database will change its execution plan. So here, if we query on store ID 1, we can see that just 1% of the rows meet that criteria. And so the database would like to use an index. Whereas if we query on store ID 2, 90% of the rows meet that criteria. And so here, the database would like to do a table scan because that's going to be faster. So the database, again, changes its execution plan based on the actual values you're querying on and what the underlying data looks like, which is pretty neat. Another interesting field is histogram bounds. So the database orders all of the data in your column and slices it into, it sorts it and slices it into different chunks, and it stores the bounds of those chunks. And what that's really useful for is range queries. So if we're looking for all of the products with quantity less than 5, so ones that are almost out of stock, what this will do is we can see that 5 falls between 0 and 9. So there are going to be very, very few rows that meet that criteria, that have a quantity less than 5. And so again, the database would want to do an index scan here. Whereas if quantity is greater than 5, that's going to have to cover a lot of the table. So the database would here do a table scan. Another shortcoming of this approach is that when we query PG stat statements, often we'll get something back that looks like this. So the value of it has been replaced with a question mark. And it does this because it's normalizing queries. It's grouping many queries together that are similar. But what happens here is that we lose a bit of data. And as you saw before, the values that we're querying on actually really do matter for speeding up queries. And so that brings me to V2. So V2 takes a very different approach, and its main goal is to address a lot of the shortcomings that we just talked about in version 1. So starting with the collection process. Version 2, instead of using PG stat statements, actually uses your log file. And it does this to actually get the full text of queries. And so there's this setting called logmin statement duration that you can turn on and have it log all the slow queries in your database. And from that, we can parse the logs and actually aggregate the data very similar to PG stat statements. But this time, we have two but this time there are two different things that we now have. One is that we have the actual text of the query. We don't have a query with a question mark in it. And we also now have multiple samples. So we can use many, many different samples to try and optimize our indexes. Another big shortcoming is that we are duplicating planner logic. If we think about what the planner does on a high level, it takes in a query and a set of indexes, and it determines the best indexes to use for that query. It's limited by the indexes that you've created in the past. What we'd really like it to do is to consider all possible indexes. And if we can get it to do that, it can then give us the best indexes possible to use. So, how do we make this happen? Luckily, there's this hook in Postgres called the getRelationInfo hook. Someone added this hook 10 years ago for a project called Index Advisor. And the description of this hook is right here. Here's the comment from the source code. And so what it does is it allows a plugin to editorialize on the info we obtain from the catalogs. Actions might include altering the assumed relation size, removing an index, or adding a hypothetical index to the index list. And that last part is what we're most interested in. We want to add some hypothetical indexes to make the database think that all indexes are there. And as luck would have it, there's another great open source project called HypoPG, and it allows you to create hypothetical indexes. It gives you commands to create them, and then what you can do is run and explain on your queries, and it'll tell you if a hypothetical index was used in your query. So it's not actually creating them, they're not actually taking up any space. The neat thing about this extension is that you can install it without restarting your database, so you don't have to worry about downtime. And the hypothetical indexes are ephemeral. So when you disconnect from the database, they're gone, and they don't affect any other sessions within your database. So they're limited to the current connection. So this was done in a very, very nice way. So let's revisit the query from before with this new approach. First, what we'll do is we'll run and explain on the query. And what we're really interested in is the final cost. You can see here that it's 1,000. You can also see that we're doing a sequence scan on products, and it's filtering on the two conditions in the query. And we're going to take that cost and add it to this table. And now we're going to add some hypothetical indexes. We're going to look up all the columns in the query, and we're going to add hypothetical indexes on those. So in this case, on store ID and brand ID. And we're going to run explain again. And again, we're interested in the final cost. This time it's 50. But we're also interested in to see if one of the hypothetical indexes we created was used. And here you can see that one was. And if we look at the index condition, we can see that it's the brand ID index. And we're going to add that to our table as well. And then we're going to do this one more time. And this time we're going to do it with multi-column indexes. So with multi-column indexes, the order matters. So we're going to add it to both store ID, brand ID, and brand ID, store ID. And we're going to run explain again. And for the sake of this example, let's say that we ended up with 45 as the final cost, and we ended up with a hypothetical index on brand ID and store ID being used. So now that we have all this data, the question is, what column do we add an index on? So we can see that adding a single column index significantly reduced the cost, but adding a multi-column index only reduced it slightly. And so in this case, we would just want to add a single column index because of the trade-offs that we get with adding more indexes. So this approach is also available as an open source project, one specifically for indexing called Dexter. The way Dexter works is that you give it a log file, and the recommended way is to actually stream your log file into Dexter, and this way it can actually give you real-time suggestions for indexes. You also give it a database connection, so it can create the hypothetical indexes and run the explain. Here are 3 useful options for using Dexter. The first is the create flag. So by default, Dexter doesn't actually create any indexes. It just prints them out for you to create themselves. So it acts more as an advisor. Once you've developed, some trust with Dexter, that it actually works on your specific workload, you can then pass the create flag. And it'll actually create the indexes. It creates them concurrently, so it won't lock any of your tables while it's doing its work. Another option is exclude. So there are certain tables that you may want to exclude from automatic indexing. One example might be very, very large tables, because the indexes might take up a lot of space, either on disk or in memory. And so you don't want it to automatically index those. You may also have tables that are very, very write-heavy. And so you don't want to take the performance penalty of adding more indexes on those tables either. And so you can pass those to the exclude option as well. A third option is min time. So you may be running some one-off queries on your database, and you probably don't want those queries to be indexed. And so what you can do is use this min time option to specify a minimum amount of time for queries to run. And so this allows you to only index queries that are taking up a lot of your CPU cycles on your database. So let's take a look at some of the shortcomings of this approach. Let's say that here are two queries that we've collected and analyzed. We have select star from products where A is 1 and B equals 2, and select star from products where B is 2. If we analyze the first query, what might happen is that we find that A is the best index for this query. And with the second one, we'll find that B is the best column to index. And it might be the case that A is only a slightly better column to index than B in the first query. And so if that's actually the case, we don't want to add 2 indexes. We just want to add 1 on B, because we're going to get most of the benefit out of indexing by just having that 1 index. So the approach right now is very greedy. It processes queries one at a time. And what we're really looking for is more of a global optimum, because we're trying to optimize across all queries on our database. So in this scenario, what we can do is actually figure out the top n queries. So let's say the top 5 queries, the top 5 indexes for a given query. And once we have that, we can then optimize across all of the different queries on the database. And we can use the cost reduction that each index gives as kind of a weight in this optimization problem. Another limitation is that right now it only works with B-tree indexes. However, support could easily be extended for other index types in the future. Also, it doesn't work with expression indexes or partial indexes. And partial indexes are actually where I think some of the more interesting work will be in the future. If you're not familiar with partial indexes, they allow you to index just a subset of your table. So you can specify a where condition and just have an index on that particular condition. And rows that don't meet that condition won't be in your index. And so this allows you to get very, very fine-grained with your indexes. You can actually create many very, very small indexes that are specifically tuned for your workload, so the values that you're specifically querying on. So one example could be you're looking for out-of-stock products, so products where quantity equals 0. If you're running this query often, you probably don't need to add an index. You probably don't need to index all of the products within their quantity, because you're probably not doing any other queries on quantity. And if you're doing a query like quantity greater than 0, it's going to do a table scan, because that's going to cover a lot of different products. So in this case, you could just do a partial index where quantity equals 0 and have a very, very small index. And it would just be the products that meet this criteria. So it could be very, very tuned to your workload. Another shortcoming is that we're adding indexes, but we're not removing any. We're not doing any cleanup. And so one easy thing to do would be to remove any unused indexes. Postgres has stats on index usage, and you can easily get those and figure out what indexes you're not actively using. One caveat with this approach is that you have to consider the replicas as well, because indexes are shared with both the primary and all replicas. So you need to aggregate the stats across all databases in your cluster and combine them together to actually remove these indexes. Another limitation right now is extension support. If you run your own self-hosted Postgres, it's very, very easy to install Dexter and whatever extensions you would like. However, if you're with a hosted Postgres provider, many of them just support a limited number of extensions. And with some of the biggest Postgres providers, hypopg is not currently one of those supported extensions. And so what you can do is what we do at Instacart is actually spin up a self-hosted instance on a regular cadence, say once a month, pull all of your data into that self-hosted instance, download the log files, and then run Dexter there for index suggestions. It's far from ideal. You lose out on the real-time aspect of it, but it's one way to see what columns to index. If any of you here work for one of those hosted Postgres providers and you get a little bit inspired by this talk, it'd be great if you could help make that happen. So now we have a solid way for the database to index itself. And with a bit more work, I think we could actually get an approach like this to ship with Postgres. Before I wrap up, I wanted to say a big thanks to pgquery and hypopg. These are two really great open source projects, and without them, this work would have been impossible. And finally, I wanted to invite everyone here to get involved. So please go download Dexter, try it out on your own workload, give feedback, help contribute to the project, and together we can make manual indexing a thing of the past. Thank you. Questions?
So there are a couple of limitations on using a cost-based approach to decide which hypothetical index to choose. Is that certain kinds of queries do not report a realistic cost. Abort-early queries, for example, do not actually report their final cost correctly. That's a query where Postgres is expecting to get all the rows you need for a limit early and come back in it.
Yep.
The cost it'll report is actually the total cost of the query, not the one that it expects to get. The other area where queries often have wrong approaches for data types that have very primitive estimators. Where it's got a flat estimate, say 0.5%, like we do for some geographic types, etc.
Mm-hmm.
Is this anything you've looked at all in terms of how to work around that?
There hasn't been any work so far for those particular cases, but I think that's a great place to work on in the future.
What's the performance of Dexter like? I know a client who have a lot of log files because they have big systems and they're busy.
So the question is, what's the performance impact of
Dexter, just how much log can you consume in an hour? Or how much would you?
Sure, yes. So the
They produce hundreds of gigabytes of log a day.
Yep. So the question is, are there any concerns around the amount of log volume that this would produce? And the question is certainly, depending on,
Not produced.
or produced, yeah. So depending on what your workload is, it's definitely something that you have to be aware of. What you can do is actually try setting the value of logmen statement duration to be.
No, I haven't been clear with my question.
Sorry.
They log everything.
Yep.
So there's hundreds of gigabytes of log.
Gotcha.
So how long is Dexter going to take to read it?
Sure. Yeah, so if there's, the question is, how fast can Dexter process log files? I think that's just something that you'd have to try out on your own workload. Usually with what we're logging at Instacart, it can do a couple of days worth of log files in usually a couple minutes. But it's certainly not, we're not logging that much data. So, but I think that's another thing that could definitely be tuned over time if it's just rewriting some of the code to parse those things out. How many indexes have we created at Instacart? So at Instacart, we do the approach where we actually use it more in an advisor capacity. So the tool itself hasn't actually created indexes, but we've found probably 20 or more indexes in the couple of times that we've actually pulled it to, that we decided to add to it. Yep.
So you took into account the duration of the query, but what about the frequency of, say, the type of query? Like, do you take into account any other aspects?
So what it ends up doing is it'll group all of the similar queries together based on their parse tree, based on a hash. And then from there, typically the way that I'll use it is specify the minimum amount of time that we want a query to run, so the minimum amount of CPU time that all of the queries together have taken. And then from there, basically try to optimize all of those. Yep.
What about if you have a group of queries that only run like once a week, but they're all reporting queries? So would you potentially be over-tiering reporting queries that run very, very frequently at the cost of other queries that run more frequently?
Okay. Sorry. So the question was, if you have queries that are running relatively infrequently, but they're taking up a lot of time, could you be over-indexing on those particular queries? And the answer is certainly. And I think that's where it really is up to you to really tune the minimum amount of time that you specify. You could also, I guess, exclude queries on, you could maybe exclude specific queries. Could be some future work for this project of, let's say, your analytic queries, you have a comment or something in the particular queries. That could be another way to approach it in the future. Not right now, but that could certainly be something that's easy to add. In the back.
You guys thought about how you can sort of try to estimate the cost of adding an index, and like the right cost of adding an index?
Yeah. So the question is, have we tried to determine the right cost of actually adding an index? And the answer is not right now. So yeah, that could be another area for future work, is really trying to optimize on the total database time that you're saving. Can you say that again?
The SQL has bind variables. You would see the records where ID equal to bind
Yeah.
variable. How does it create index? How does it determine this activity and value?
So the question is, how does it handle bind variables in your logs? And the answer is, unfortunately, it doesn't do that right now, because there's no way to actually get the values of the query. And with this approach, you actually need the full query, because you have to run and explain on it. So you actually need queries with values in them.
They're actually in the log, but that really is kind of ugly to put it together.
Okay, yeah, so it doesn't try to, right now it doesn't try to combine them. So yeah, I mean, if that's the case, then it, probably with more work, that could be possible.
They log kind of the next line down, basically have to parse and bind and execute, and there are three pieces to every statement. And it's a nuisance because you get 3 times with everything.
Yeah.
Sometimes it's not that part, but getting the time that.
In the back?
So, is there any thoughts on using PG stat statements to either augment or replace the log parser?
The question is there any thought around using PG stat statements to replace the log parser? And the answer is yes, that's actually an option. So you can actually pass an option for it to use PG stat statements. So for the times where it actually doesn't return a normalized query, you can actually get the full text back. I'm not actually sure when you get the normalized query, because we grab from PG stat statements every 5 minutes at Instacart, and some of the time the queries get normalized, some of the time they don't. And so if you're running it like that, usually you can get a pretty good sample of ones that have not been normalized. Other questions?
Yeah, a lot actually, but
So, prior to HypoPG existing, we developed a fairly manual tool to do this, David Wheeler and I, using basically just using a replica.
Yeah, I think that work can definitely fit into the kind of the global optimization approach to really try to figure out what are going to be the best indexes overall if you sort of are trying to limit the actual number of indexes that you're adding. So I think that makes sense. Anything else? Cool. Well, thanks everybody.